TTL Computer 2. Today we're going to be taking a look at some updates to our ALU circuit. And it may be beneficial to rewatch our original ALU circuit video to refresh yourself on how that all works. Um, but we're really going to just talk about the decode and latch section of the ALU. And I'm not going to go rehash those details, but at the high level, we have two decode uh, operations occurring. One is the decode for the ALU uh, control signal bits, ALU 0, 1, and 2, and that specifies the operation that the ALU is going to be performing. And all of these chips, one, two, three, four, five, six chips are just doing the decode logic, the combinatorial logic to take the three-digit ALU control signal and generate the signals that the 74181 requires. And then we use one chip also as a carry flag latch. And so those are the functions that we have. We had 8 chips, right? One, two, three, four, five, six, no, 7 chips. And that's a lot of chips that we have to put on our board. So what we would like to do is replace all of that with this one single chip to do one single chip to rule them all. And you can see we have our ALU 0, 1, and 2 signals as input. We have our carry signal input. Then we have all of our decoded signals that will drive the 74181 chips. So you say, Charlie, well, how are we going to do that? So we're going to do that using a GAL. And that's a generic array logic chip, or kind of more commonly known a programmable logic array. And so just briefly, I'm not going to go into this in much detail, but briefly, these chips are pretty much out of production for, I don't know, 10 or more years. And but they're still pretty readily available, and they're very convenient just for this purpose. It's kind of an easier way to replace a lot of combinatorial logic with just a single chip. And these chips, of course, need to be programmed. So what we're looking at here is my program that I developed to program the GAL for our needs. And just briefly again, you can see up here, it's just defining the GAL chip that we're using, a GAL 16V8. This section of the code defines our input signals, our input pins and signals, and our output, signals and pins. And then this section is our logic equations for each of the signals. And you can see down here that these are the operations that are allowable in our logic equations. We have, star is and, plus is or, and the slash is a negation. So as far as our logic equations go, this was generated by digital, if you remember. Again, looking back at the original video, we defined the truth table. And from that truth table, digital did two things for us. It gave us the equations, the logic equations that take the inputs to the outputs based on the truth table. And it also gave us a corresponding circuit diagram that implemented this logic. But you can go back again, look at the old video to you refresh yourself on how that stuff worked within digital and how we used it. Okay, so this was our program that I developed, and then I compiled that up and burned that into the GAL. And the next step was to go to our testing jig. And if it wasn't kind of evident, our testing jig is a pretty useful device, and I've already used it 2 times for purposes other than testing our circuit board. So this te our testing jig really is going to have usefulness that is going to go beyond, our TTL computer too. But I used it to test those fancy retro hex displays that we're going to use, and then I also used it here to test the gal. So you can see I just used a small breadboard and patched that all in. So we had the output signals are being displayed to our LED display, and then our input signals are all wired to this switch. Okay, and then one of the things that comes as the output of assembling the GAL source file that we looked at is it gives us it produces a diagram of the GAL, and it has all of the pins defined. So you're kind of looking at a printout of that down here, where it has VCC, and then it has all the other signals for one side of the chip, the output signals mostly. And so I've used that as a cheat sheet here, and I put some tape on the LED display and just, called out the signals so they're easier for me to see, right? M, CN, S1, S0. This is NOE. This is P, NOE, and then this is the carry flag latch bit. Okay, so that's how I had the testing jig set up. Now, we didn't really have to do a test plan for this because the test plan was the truth table, again, that we had put together in our digital simulation. And that really just I had to run through the truth table. I actually ran through it twice just to make sure it was good to validate the operation of the chip. But that passed and was all successful. Okay. And then, all right, so that got us here. Again, this is a duplicate of that of the pinout diagram that was generated by the assembling of the GAL source program. So I used that as a diagram to wire this up. So what I'm doing here is I'm creating a digital simulation of our GAL chip, right, to replace all those 7 chips that we had before to the one to rule them all here. So let's open this up. And we can see that this looks a little bit familiar. Again, if you think back to our video where we used the truth table and then we looked at we used the create a circuit function. This is that circuit that digital generated for us based on our truth table. So I put that back here. Here's our inputs, ALU 0, 1, and 2. Then I had to add in the D latch for our carry bit. Now, this is something that deviated from the original version that we had. The original version was a D latch, so it was not a flip-flop. There was no clock signal involved, just an enable signal. So the function of this chip, this new of the GAL, is going to be a slightly different from what we had developed in the digital simulation before. But so we need a clock signal to clock in, the input and to latch that in. And that signal is going to be is down here, right? So this is the active low output enable for our ALU output, and we want the clock signal to be the inverse of that. So when this goes low, POE is going to go high. So right as soon as the ALU operation begins, and that's signified by any of the bits, ALU 0, 0, 1, or 2 going high. As soon as any one of those bits goes high, the active low output enable goes low, and we will have the positive output enable go high. And then that's what we're going to use as the clock signal, right? This is going to be routed back in as the clock signal. So the carry flag will be latched in at the start of the ALU operation. Okay, so that gives us, right, that's where we got the circuit, and right, that leads us, to our GAL. And we have the POE signal that we just spoke about. and that is routed up and is the clock for the carry in latch. Okay, so that is that. And then our final stop is just go back to our digital simulation and test that this is working with the new GAL implementation. And we can just start that now. And we are running, and we can see that our regression test program is running and cycling through, and that went through all of our tests successfully. So we have our new one chip to rule them all GAL decoder for our ALU. That's greatly simplified our ALU circuit for our build, and we've validated that's all operating correctly. So that's it for today. I went over at a very high level about the GAL. If there is interest for me to spend a little bit more time in looking at the GAL and talking about that a little bit more, how it works, and going into a little bit more details about the programming, as well as what I use to actually to assemble that, because you have to take the source program and you need to use an assembler to generate the file that you need to download to the GAL. If there's interest in me going into that in a separate video in a bit more detail, please indicate that in the comments, and if there's enough interest, I will do that. But I've already received the memory card PCBs back from JLC PCB. I'm going to begin populating those next, and that will be our next video. So until then, thanks for watching.